Okay, so thank you for the organizers for the invitation, and it is a great pleasure and honor for me to open this conference, even though it is in this way. So I would like to present a recent work that I did with Wilfried Gangbo from UCLA, and we started this during my postdoc there, and we put the paper to the archive very recently. So this will be on the master equation arising in Minnifield games. Please feel free to ask questions and interrupt me anytime. So just as Dima said, raise your hand or write a question in chat and Diogo will let me know. Okay, so the content of my talk is as follows. So since I'm the first speaker, I would like to recall what are Minnifield games. And quickly, I would like to arrive to the derivation of the master equation. I will do all this in the deterministic setting. And I will focus then on so-called potential Minnifield games, which are linked to optimal control problems in infinite dimensions. And I would like to highlight during the talk some differences between the so-called vectorial and scalar master equations. And the main focus of this talk will be on displacement convexity of the data that I will explain, and I will try to explain how this gives us the sufficient regularity to justify all the derivations that we need for the master equation. Okay. So just quickly, Minnifield games is a recent theory that was introduced now like 15 years ago already. It was introduced by two groups, a French group composed by Lastry and Lyons, and a Canadian group composed by Keynes, Zhuang, and Malame, who proposed this theory to somehow understand limits of Nash equilibria of n-player differential games when the number of players tends to infinity. So this was the main idea behind the two, both of the works. And then many researchers came in, and it became a very popular and very extensive field of study in the past 10 years or so. So this, in a nutshell, very basically, this Minnifield game problem can be formulated as follows. So we have a population of agents who would like to move in the space in an optimal way. They would like to optimize some kind of cost function. So I will always work with such infimization problem. So this is an extra minimization problem where the cost of an individual agent is depending on the distribution of the others. So this, I will always focus on this separable case when you have a Lagrangian and you have a coupling function. And I chose to set this kind of direction for the system. So I will prescribe the initial cost for the agents, and both of them are depending on the distributions. So an agent, what he or she has to do, it is about the prediction. So they have to predict the evolution. So what would be the evolution of the agents in time? So what would the other agent think? And with respect to this evolution, this prediction, they solve their optimal control problem. And here, once again, the data will be, so I will work in the d-dimensional Euclidean space with my Lagrangian and coupling function and so on and so forth. I chose for the measure variable rho, the space of probability measures with finite second moment. And I will use throughout the talk this kind of ball in the space of probability measures, which is a set of probability measures having second moment bounded by R. Okay, and of course the final distribution of the agents is also described. So at time capital T, this is described. And if we try to look at this optimal control problem as a finite dimensional optimal control problem, we know that under differentiability conditions, on the value function, the optimal control would be given in a feedback form, and it will be this term. And the u tilde value function solves Hamilton-Jacobi equation. Like this is all formal with an initial condition. And if everybody is thinking rationally, then the evolution of the agents is given by this vector field. So the density is transported. So this is just the conservation of mass equation, Euler's equation of mass conservation. The continuity equation is transported along using this velocity field, and it is a backward transport if you want. And this system fully characterizes an equilibrium situation. So if the prediction was correct, so if rho was the same as the evolution using this, the evolution of rho using this vector field, then we are in an equilibrium situation. So if we are able to find a solution for this system, that solution u tilde and rho describes an equilibrium. Okay, and here the Hamiltonian is naturally associated to the Lagrangian by the Legendre conjugation in the second variable. Okay, so I am already going to master equations. So all these so far are formal, all these derivations. And I would like to do some kind of justifications for this. So the master equation was introduced by Lyons, and he's inspired by such equations already out there in statistical physics, if you want. But this is a different sort of equation. So this is a non-local Hamilton-Jacobi equation set on the physical space, which is the time cross Rd, and it has the variable rho will enter in the equation as well. So what I will mean by this, I will explain in a moment. And the purpose of this equation of Lyons was to contain all the information of a Minnifield game system in a single equation, which also contains the information what would happen if you would change the final distribution of the agents, which is prescribed. Okay, so the basic idea is that let us look at the Minnifield game system that I wrote on the previous slide, and denote, that is why I called that value function u tilde, because I will use the variable u for the master equation. So let us call u at capital T, which was the fixed finite time before, and mu, which was the fixed final distribution of the agents. Let us define a function which is depending on these objects, and which is the value function of the Minnifield game from the Minnifield game system when we set the final value to be the final distribution to be mu and the final time to be t0. Okay, and we must have, so we have a sort of dynamic programming principle. So we must have that this function, this master function that I will refer to as a master function, will be the same as the value function if we go back along the curve rho t. And we can put the natural question that is there an equation satisfied by this little u? And how can we do that? We just differentiate in time, basically. So if we differentiate in time, mind that the x derivative of this little u, it is the same as the x derivative of u tilde. And moreover, we will have this kind of relationship. So if we differentiate along the optimal curve because of this relationship, we will have that this has to satisfy the right-hand side of the Hamilton-Jacobi equation in some sense, right? And since the x derivative of u tilde and little u are the same, we have this right-hand side. So in order to write an equation, we would need to understand the sort of chain rule. So we would like to develop this time derivative here. So this is this is possible, for instance, using the theory of optimal transportation. And I recorded some information from optimal transportation. So in my setting, I will work in the metric space P to RD, equipped with this W2 distance, which is referred to as a Wasserstein distance. So this can be written in a standard way using this minimization. And I will, at some point, I will pass to random variables. So I wrote also this formulation using random variables. So the first one is using transport plans, and we are solving it as a linear programming problem using transport plans. And the second one is find basically optimal couplings for probability measures using random variables. And for my Hilbert space that I set, where I take my random variables from, I set it to be a non-atomic probability space. For instance, the cube 0, 1 equipped with the Lebesgue measure restricted to that cube. Okay. And it is well known from the theory that this optimal plan can be realized as an optimal map, which is a gradient of a convex function if the measures are absolutely continuous. So it is reasonable to try to think about differential geometric structure of this space. And this was a revolutionary result initiated by Otto and then developed in full rigorosity by Ambrosio, Gigli, and Savary in their book. So it indeed, this space as a metric space has a differential geometric structure. And you can speak about tangent spaces and tangent bundles like closure of smooth gradients with compact support in L2 with respect to the measure. So basically, so this is somehow the idea is coming from Brenier's theorem in some sense, because that is why you are looking for this kind of gradients to have velocity fields. Okay, and so I would like to understand derivatives of functions on this space in order to be able to do chain rule. And there is a good notion of subdifferentiability and superdifferentiability of functions on the Wasserstein space. So I will try to use as much as possible the intrinsic differentiation on the Wasserstein space, and I will make some comments on the links to the differentiation in the Hilbert space. So what we mean by a subdifferential of the function at the measure, this will be an L2 function with respect to the measure, such that you have this sort of first-order Taylor expansion using optimal plans and up to a liter error. So you have this kind of inequality, which is coming typically from convex analysis. So it is developed in abstract settings in convex analysis. And the superdifferential is defined in a very similar way. And in particular, we can compute the superdifferential using the subdifferential of the negative function. And we say that the function is differentiable at the measure if these two sets do intersect. And in that case, there is a unique element of minimal L2 norm with respect to the measure, also belonging to the tangent space that we defined previously. And this we will call the Wasserstein gradient of the function at that point, at that measure. And we have the theorem that we wish for. So if we give a geodesic in this space, we can write down a chain rule. So if you have a function which is differentiable along the geodesic, then we have this formula for the chain rule. So we can compute the time derivative of the composition as the Wasserstein derivative times the velocity field. So this is like an inner product in the tangent space. So it can be seen as an inner product in the tangent space. Okay, and just to see some examples that we will have in mind and how this works in practice. So for instance, a typical example in Minnifield games is that if we take coupling functions and initial data functions to be potential plus interaction energies. Of course, we can take way more complicated objects, but these are very typical objects and they have physical motivation because this stands for the potential energy and this is interaction energy. So if you have two C1 functions which are behaving nicely at infinity, so the integrals are meaningful if we take measures from P2, then we can compute this. So if they are C1, we can compute the function will be also C1 with respect to this differentiation that I described. And the Wasserstein gradient will be the gradient of the potential plus the convolution of the gradient of phi1 with the measure, provided that we have so this there is a typo, so phi1 should be even here. If not, you have to work a little bit more to find this gradient. If you have the even property, then you have some simplification. Okay. And I would like to highlight that this object is defined only on the support of the measure. And if you would like to speak about its value, so this is like a vector field, and if you would like to speak about its value at a different point from the outside of the support, we will need to make some sort of extensions. So in this case, even if I consider a Dirac delta in this example, this object would have a natural extension if phi1 and phi2 are defined on the whole RD. So this already gives you like what should be a good extension. But in general, you have to be very careful that this object is defined only on the support. And in order to speak about its general value, you have to do an extension if you can. So for instance, if this object is Lipschitz on the support of the measure, then you can do like a Lipschitz extension, for instance. But of course, there are situations when that this is not possible. So imagine that you have here just the potential energy, and this phi0 function is differentiable only on a ball. Then if I take a measure which is not supported on that ball, the capital U function will be not differentiable at that measure. And in particular, that object, the gradient object, is making really sense on the support of the measure. Okay, so with this in hand, this tool in hand, let us go back to that differentiation that we left on the second or third page. So let us recall that we needed to compute this total derivative, time derivative. And this is in the measure variable, we are using formally this kind of calculus that we developed. We know that the curves are having velocity field TPH composed with dxu, and dxu, it is the same as dxu tilde. So here we can simply replace the master function itself. So we will have this non-local term entering in the equation. So the master equation reads as follows. It is this non-local Hamilton-Jacobi equation in which we have non-locality in the gradient variable with respect to the measure. Okay, and it is equivalent with the initial condition coming from our original problem. And why this equation, right? So as I said, Leon's had this nice idea to develop this equation, not only because it contains all the information of the Minnifield game system, but actually turns out to be a very useful tool to showing the convergence problem of n-player differential games to the Minnifield game system. And I refer to this very nice paper on the master equation in a way more general framework, having noises, by Cardaliaga, Delarue, Lasky-Lyons, where they emphasize this use of the master equation on showing this convergence problem. And there are different other papers that I forgot to mention here by Delarue, Laker, and Ramanan, for instance. They study even central limit theory and so on and so forth for n-player differential games using the master equation. So this is a very powerful tool if we want to understand such problems. And our objective in this talk is that let us forget about all the noises. So we are working in this very deterministic model, and let us try to find some sufficient conditions on the data for which we can produce classical solutions for this master equation for arbitrarily long time. And what I mean by classical solution, that this function is differentiable in all its variables, and the equation is satisfied in a pointwise sense. And I would like this time horizon to be arbitrarily long, independent of the data. Okay, and let me recall some results from the literature. So first result in this direction on the deterministic model is by Gangbo and Shuye. from 2015, who studied this problem with a specific Hamiltonian, which was exactly this one. And they had to impose smooth conditions on the data, and they are able to show well-posedness of the problem. Then there is an extension by a PhD student of the two authors from here, Sergio Mayorga, who generalized this result for general Hamiltonians, which can be even non-convex. And the games might not be potential games, as it was the case here. And this is also a short-time result, as we could expect, because you have a lot of degeneracy. So, for instance, the Hamiltonian is not convex in the momentum variable. And using Hilbert space techniques that I will also describe, that there was more or less a parallel work, like a couple of years later, by Ben-Susan and Yam, who obtained also short-time existence using Hilbertian techniques for this quadratic Hamiltonian. Then I already mentioned the fundamental paper of Cardellaghe de la Rue-Lascaux in the presence of common and individual noises. And in their paper, they can have a global existence under the smoothness conditions on the data, convexity of the Hamiltonian in the momentum variable. They are morally working with quadratic Hamiltonians. So they have to have more or less quadratic, so slightly general than quadratic, but more or less quadratic. And they have to impose a crucial so-called monotonicity condition on the data that I will also describe later. And like this, they are able to show arbitrary long time well-posedness of the equation. And then using probability techniques, there are two more results, or even more. So sorry, I am not fully. So I am not. I didn't intend to write a full reference list. Sorry if I missed someone. So there is the textbook of Carmona de la Rue describing interesting probability approaches to deal with such master equations in the presence of noise. Then there is this paper of Ben-Susan, Greben, and Yam, who use optimal control techniques in the presence of noise situation. And Chassagneux, Christian, de la Rue even considered degenerate noises, and they assumed also monotonicity on the data, and they could also show global in time well-posedness of the master equations. And there is a follow-up work by Chen-Chen Mu, Jianfeng Zheng from 2019, who can relax the conditions, the regulatory conditions on the data F and G from the previous paper, from here. And they develop a nice theory of weak solutions for equations in the presence of possibly degenerate noise. Okay, and I believe that Chen will speak about these results later this week. Okay, and the main tool in the paper of Cardellaghe de la Rue-Lascaux is PDE techniques. So you look at the Minnifield game system and the classical finite dimensional Minnifield game system. You would like to understand the regularity of the value function if we perturb the final condition, the measure, and using heavy PDE machinery, you can show the regularity in the measure variable, and then you can justify this formal computation that I also did. In our case, this kind of lack of non-degenerate noise make any trial of PDE techniques just impossible, because we are not able to get regularity on the solutions of the finite dimensional system. So what we will do, we will go to a variational approach, and in particular we will work with potential games, and we will try to understand the regularity of value functions in optimal control problems using optimal control techniques rather than PDE techniques. Try to translate this kind of regularity that we get on these value functions to the master function, to the regularity of the master function. Okay, so what do I mean by potential games? So I mean that the data f and little u0 are derived from some potentials. So the standard derivative of little f will be the Wasserstein gradient of some given potential function f, and the same for little u. And I will lift my finite dimensional optimal control problem to the space, to a control problem on the space of probability measures. For that, I will define on a slight extension of the tangent bundle, I will define a Lagrangian, and I will define on the cotangent bundle a Hamiltonian. And I will be looking at this kind of optimal control problems. So if you are familiar with the Benamou-Brenier action minimization problem of the optimal transport problem, this is, morally speaking, very, very similar. So in that one, you are doing this kind of minimization problem of the kinetic energy. So this is, if you have here just V squared rho, and you forget about capital F and capital U0, and you prescribe initial density as well. This is nothing else than Benamou-Brenier. And this is a variation. So this kind of approach was used a lot in so-called variational physics. Also when this coupling function was local. So in our case, since we are assuming some sort of regularization effect, these coupling functions and initial data functions has to be in some sense regularizing, so they will be non-local operators. Okay, but I am looking at this optimal control problem in the space of probability measures. And I would like to understand the solution and the regularity of the solution, which I denote capital U. And I would like to link it to the master function. So here, the idea is that if I can show that this object is differentiable in the measure variable, and I am able to say that at every measure, this Wasserstein gradient is the gradient of a potential function, then this potential function is the candidate to be the solution for the master equation. So like I can also write this very formal differentiation. So this would mean that the first variation in the L2 sense of the function has to be this one, right? This little u. So this is what it formally means. And this is, I will try to justify why this is a good candidate to be the solution for the master equation. Okay, and if we work with this optimal control problem, this optimal control problem is a little bit, it is producing an equation which is nicer than the master equation. Why? Because this is like a more standard Hamilton-Jacobi equation just set on the space of probability measures. And this is not having that non-local nature as the master equation. Okay, and if we look at this as a value function, it is almost straightforward to show that this is locally Lipschitz and displacement semi-concave in the measure variable. I will speak about displacement convexity in a moment. And the question is that how do we get more regularity on this value function? Because I would like to understand whether this is differentiable or better with respect to the measure variable. And notice that we are looking for this kind of relationship. So our candidate will be, as I said, the first variation of this function. So like that, it is not really enough to have one differentiability. So differentiability of the function only once of the capital U function. So we are looking beyond the first order differentiability of this function in order to be able to have like a classical solution for the master equation. This is the philosophy. And to be more precise about this potential function, this is how we define the candidate for the solution for the master equation. So I am having this optimal control problem where my optimizers are curves in the Wasserstein space. So imagine that I can find a unique minimizer for this action minimization problem, optimal control problem. And what I define this little u function to be this value function for this finite dimensional optimal control problem. Then on my data little f and little u0, I use the optimal curve that I got from the previous problem. So if I give you this sigma, which is a curve, which is having so at time little t, this is mu. Then I construct this cost function, which is depending here on time and space, and I solve this optimal control problem. and I claim that this is the good candidate for the master equation. And like this is always defined everywhere. So here you see that I am not taking only points x in the support of mu, but I am taking generic points x. Okay, and since this is a finite dimensional optimal control problem, the regularity in time and the space variables are straightforward. So we can study using classical theory. Okay, and notice that if u is differentiable at x0, then the value function is producing the optimal feedback control for this problem, and this has to have this form. Okay. Now, if u in the previous problem is also differentiable, then the optimal curve can be written like this, using the Wasserstein gradient of that value function. Okay, and let us notice that if you would like to solve this continuity equation, so given this velocity field, if I fix mu as a final measure and I try to represent the solution along a flow using this vector field, this is somehow similar to the flow equation, right? So in particular, if I take a Dirac delta for mu, for instance, then the curve that I produce here, it should be the same as gamma that I produce here if I start with that point sitting at the Dirac delta. So you have to have this kind of correspondence between the continuity equation and this optimizer here if you sample the points x from the support. And in this case, if you have, so these kind of curves have to be the same, and if you have strong convexity of the Hamiltonian, you have to have that the gradients have to be the same. So this is how we obtain that the gradient of this value function, little u, has to be the same as the Wasserstein gradient of the big value function, capital U, at least on the support. So notice that like this, if we can show lots of properties on this little u function, for instance, differentiability with respect to the measure, and the other guy is also differentiable with respect to the measure, this object produces a natural extension for this gradient on the whole RD, not on the support only. So this is the main, this is the heart of our analysis, basically, that we would like to understand these two optimal control problems. This is the link between them, and then try to produce a regularity theory to show that all of these objects are regular with respect to all the variables. Okay, and I would like to make here a remark on the so-called vectorial master equation, which is just formally the Wasserstein gradient of this Hamilton-Jacobi equation. So if you look at this Hamilton-Jacobi equation and you take formally a Wasserstein gradient, you will have a vectorial conservation law, because you are taking a derivative of Hamilton-Jacobi equation. So this is, in finite dimension, this would be a sort of compressible Euler equation, if you want. So this is this equation, which is referred to as the vectorial master equation. And I would like to make very clear that this is not the same as the scalar master equation. So there are huge differences between the two equations. In particular, if we have this gradient to set to be a function, then that function solves this vectorial master equation. And in this scenario also we have that in general this is not defined outside of the support. And notice that by the previous reasoning that we had, if we produce a regular solution for the scalar master equation, then the spatial gradient of it has to be a solution for this vectorial master equation. But vice versa, it's not that clear, right? So if I solve this, if I just take a derivative of the Hamilton-Jacobi equation, from there I cannot really construct yet the value function. I have to go through that finite dimensional optimal control problem, for instance. Okay, so as I said, let us go to the regularity theory. And to understand the regularity of the value function capital U, I am lifting the problem furthermore to a Hilbert space. So I know that this problem makes sense on the Hilbert space as well, mainly because you have that the P2 will be just this Hilbert space quotiented with the equivalence relation that two random variables have the same law. So they are equivalent if they have the same law. And we can study the lifted value function like this. So this is an optimal control problem in Hilbert spaces, which is nicer from the point of view of regularity theory. So if you would like to understand what is the regularity, then try to understand first what is the regularity of this U tilde. And let us remark that that you have like a one-to-one correspondence between the two problems. Since we lifted all our data are rearrangement invariant. So that means that that all these guys, so this U tilde is depending only on the law and not on the random variable itself. So this has to be the same as U at T and mu, where mu is the law of X. And of course, on the reasonable assumptions on our data, we can solve this optimal control problem on the Hilbert space. And the Hilbert space is nicer, right? Because you have the Crandall-Lyons theory, or right away to write down a Hamilton-Jacobi equation satisfied by the value function in a viscosity sense. And on the further assumptions, we can have semi-concavity estimates, so just as in the classical setting. So for instance, this can be seen in this paper of Diogo and Levaux. And yeah, we have this correspondence between the value functions, and we have a recent very important result by Gangbo and Tudorescu, who says that that actually, if this problem has a viscosity solution, then U also has to be a viscosity solution for the Hamilton-Jacobi equation set on the Wasserstein space. And moreover, you have a structure of the derivative. So U is differentiable at mu if and only if U tilde is differentiable at X. And you have a correspondence between the derivatives like this. And this is also possible for the subdifferentials. So you can write down the subdifferentials, superdifferentials, and so on and so forth. And this observation was made by Lyons also. However, Lyons introduced the differentiability of U via this kind of differentiability of U tilde. And he assumed a little bit more. So he assumed that U tilde is continuously differentiable in a neighborhood of X. Then U is differentiable on U at mu. And this result of Gangbo and Tudorescu tells you a lot more, because this is true also for the subdifferentials. Okay. And what we can say more? So can we have more regularity on U tilde? And the innocent observation that we can make is that if you have some sort of convexity in the problem, then the value function is also convex in the X variable. And if you have convex and semi-concave functions, then these are C11 on the Hilbert space locally. Okay, and what do I mean by semi-convexity in the Hilbertian setting? I just mean that you have this kind of convexity corrected by this quadratic term. Okay, and what do I mean by C11 functions on the Hilbert space? This is just the standard, the first order Taylor expansion. And this makes sense on the Hilbert space, or equivalently that the gradient is Lipschitz. And we would like to see that whether this tells you something about the value function U. So if you have a C11, so imagine that we are in this scenario that the action, the Lagrangian action is convex, and U0 tilde is convex, then and also semi-concave, right? Then we have C11 value functions in the random variable, and then how this translates to the regularity of capital U. And we have this little lemma with Wilfried in our paper that actually the C11 property on the Hilbert space versus on the Wasserstein space, they coincide just as the C1 functions. And what do I mean by a C11 function on the Wasserstein space? This is just a very similar Taylor expansion, first order Taylor expansion. But in addition, we also require that the Wasserstein gradient is lambda Lipschitz independently of the measure on the support of the measure. So this together gives us the definition of C11 function on the Wasserstein space, and this is completely equivalent to the C11 notion on the Hilbert space. So in the convex setting, so if U0 tilde is convex and the action is convex on the Hilbert space, we certainly have that this capital U value function is C11 log on the Wasserstein space. Okay, and actually we have a correspondence between these convexities as well. So this convexity on the Hilbert space translates to displacement convexity on the Wasserstein space. And what do I mean by displacement semi-convexity? We can use the definition from Ambrosio-Gigli-Savary, for instance. So this means that you have this kind of convex combination along Wasserstein geodesics. So this is the so-called McCann interpolation between two measures on the Wasserstein space, and this gives you a geodesic connecting two measures. And along such geodesics, you have this kind of convexity with respect to the metric W2. And for instance, if we are in the situation that we described for the example, if we have this potential energy and the net interaction energy, this functional will be semi-convex on the Wasserstein space, provided that the two objects are semi-convex in the classical setting on RD. Okay. And let me make a parenthesis on this monotonicity condition that was imposed in most of the results. Actually, in all of the results which did global well-posedness for the master equation. And this is like a typical condition which is used also to show uniqueness of the solution of the finite dimensional Minnifield system. So this just means that you have this kind of monotonicity in the sense of monotone operators, if you want, in the measure variable of little f and little u. And in particular, if you have the potential setting that these two guys, little f and u0, are derived from some potential. So they are, for instance, some first variation of this capital F and capital U0 functions. Then this kind of monotonicity is linked to the convexity of capital F and capital U0 along standard interpolations of probability measures, like standard convex combination of probability measures. And for instance, so this is the example that I said. So for instance, we can cook up examples of interaction energies such that the interaction energy will be displacement semi-convex in the sense of optimal transport, but it fails to produce a monotone coupling. So for such interaction energies, so this is only true. So the monotonicity of little f in this interaction energy case is true if and only if the Fourier transform of this phi 1 is non-negative. And of course, we can produce this kind of interaction terms which are having negative, at some part negative Fourier transforms, but nevertheless they are semi-convex in the classical setting, so they can produce displacement semi-convex energies. So this is like a parenthesis that I will go back to. And I would like to highlight also that this regularity that we have obtained in this convex setting, it is not enough. Because we have to have like two derivatives of this capital U value function in order to speak about one derivative of little u in the Wasserstein setting. So we are forced to go beyond the C11 property. So C11 is not enough to justify classical solutions for the scalar master equation. And of course, so since this u tilde function is linked to an optimal control problem on the Hilbert space, what we could do, we could represent the solution on the Hamiltonian flow and try to understand the regularity of the Hamiltonian flow with respect to initial conditions. And this somehow translates to the regularity of the value function. And of course, if you would like to have like C2 or better regularity of the value function on the Hilbert space, we would certainly need to impose this kind of regularity on the data. Because if the Hamiltonian flow is not at least C1, then there is no hope that we can show that the value function is C2. And surprisingly, this kind of assumptions would be too restrictive. So what do I mean by that? So imagine that, let us try to understand the second order differentiability of functions on the Hilbert space. So imagine that we have a situation when we have a function on the Wasserstein space and its lift on the Hilbert space, and we impose that this lift is C2. Then its Hessian as a bilinear form on the Hilbert space has a special representation. So this, because of the invariance, rearrangement invariance property, this has to have this kind of special representation. And we could show this lemma, which tells us that if we impose C2 alpha regularity on this function, then this matrix has to be a constant matrix on the support of the measure. So this is like one part of the Hessian, and this is the second part of the Hessian, if you want. This has to have be like a constant matrix on the support of the measure. And in particular, if we take functions which are locally representable in this sense, so these are sort of potential energies or interaction energies, if you want, then imposing C2 or C2 alpha regularity on this function on the Hilbert space would imply like a rigidity property, meaning that you have to have, because in that case, so imagine that you have only the potential energy. In the potential energy case, this disappears, this term disappears, and this term is just the Hessian of the potential. If the Hessian of the potential is constant on the support of the measure, then that means, and imagine that you take measures which are fully supported, then that means that that potential has to be a polynomial of order 2. So this gives us this kind of restriction. So if imposing this kind of regularity, we would need to work with this kind of trivial examples. And in particular, remember that the Hamiltonian on the Hilbert space is always locally representable, because that was just the lift of the Hamiltonian from the dimensional setting, right? So that means that if we would like to have C2 regularity on the Hilbert space of U tilde, we would need the Hamiltonian to be like a polynomial of degree at most 2, which is crazy. Anyhow, so in many examples, maybe that is enough, but we wanted to go beyond that. So we proposed like a regularity theory for this kind of value problems intrinsically on the Wasserstein space. So this tells us that the Wasserstein space has some sort of different structure from the Hilbert space if we look at the differentiability beyond the first order differentiability or C1. So we will introduce a space which we call C2 alpha W. So W stands for weak or Wasserstein. So this is a sort of C2 alpha property that is enough for our purposes and which do not require that these data are polynomials. And this is our main theorem that I can state here. So if we have a C3 regularity on the Lagrangian and the Hamiltonian, the Lagrangian action is displacement convex. U0 is displacement convex. And they are in this class, C2 alpha W log, then we can produce a value function which is in the same class with respect to the measure variable. Moreover, we can show the unique well-posedness, global well-posedness of the scalar master equation. So this is our main theorem. And in the last 8 minutes or so, I would like to, 7-8 minutes, I would like to just give you some ideas of the proof. And what is this space that I am introducing on the Wasserstein space? So I am imposing a C1 property of the value function. So function is at least C1 or C11. Moreover, we can have like sort of Taylor expansion for the Wasserstein gradient. So this is what we want. And these objects that we have here, so these are the second derivatives with respect to the measure. So this lambda 0 and lambda 1. So these are playing the role of the Wasserstein Hessian. These are Lipschitz functions with respect to all the variables. So this is the class which is natural on the Wasserstein space for this C2 alpha. But this is not really corresponding. So there is not like this is somehow weaker than as we feel that than the C2 property on the Hilbert space, and there is no clear implication. So this is not implying the C2 regularity on the Hilbert space. The C2 regularity on the Hilbert space is not really implying this one. So this is like a sort of different kind of regularity that we propose. Okay, and let me just go back to the example that I had at the very beginning. And in this potential energy and interaction energy case, this matrix, which is the x derivative of the Wasserstein gradient, is having this form, and the double derivative with respect to the measure twice is having this form as a matrix. And in this case, we see that this lambda 0 and lambda 1 are these objects in the previous Taylor expansion. And in order to work out the regularity theory, what we do like a finite dimensional approximation and reduce the problem to not the Hilbert space, but to a finite dimensional setting. So what we do, we are discretizing all of our measures, and we are defining this kind of empirical measures, which are sums of Dirac deltas with equal weight. And we are defining the restriction of our objective functions to this Dirac deltas. This will define functions on RD cross RDM times. And we will have this kind of nice properties. So if we have functions in our class C21 W, then these UM functions will be C21 locally, so which are meaningful. So that our definition was in some sense natural. And you have this kind of correspondence between the infinite dimensional and the finite dimensional gradients. You have this correspondence between the second derivatives. So imagine that you have a function in this class, then you can write the finite dimensional second derivatives in this way. And moreover, we will know that if we work with the value function, which is C11 in the measure variable, the restriction function, which is on the finite dimensional setting, will be also C11 on RDM. And in particular, it will produce it will produce like a classical solution to the Hamilton-Jacobi equation, where we restrict all our objects. We are restricting U0 and we are restricting the Hamiltonian as well. Okay. And here the idea is that on the finite dimensional setting, we can try to work out a regularity theory for the value function. And hopefully this will translate to the regularity of the value function in the infinite dimensional setting. And this is indeed the case. So if you are able to show that the function is C21 on the finite dimensional setting and its limit on the Wasserstein space, so you have this kind of correspondence between U and UM, and you are able to produce fine estimates on the derivatives. This will translate to the derivative estimates on the value function. So in particular, we have this kind of growth condition on the second derivatives and on the third derivatives. Then we will have so how to obtain this? So the idea is that we would like to obtain this kind of regularity estimates on the solution of a Hamilton-Jacobi equation, which is like this, and then try to translate this to the Wasserstein regularity. And the proof is very technical. So how do we do it? We are working also with the Hamiltonian flow, and the Hamiltonian flow is having this form. And we have the observation that this momentum variable gives you the derivative of the value function along the optimal curve. And in particular, we know that this is nice because U is C11. So it was C11. We would like to go beyond that. So from here, if we understand the regularity properties of P and Q minus 1, so the inverse of the mapping Q with respect to the initial condition, then we can translate all these estimates on the Hamiltonian flow to the regularity of the gradient of the value function. And this is what we do. And we have to compute nicely all the constants. So we are interested in all these constants. And this is a crucial theorem in our setting, which says that if UM satisfies all those derivative estimates, U has to be in this class. So the restriction, so we are going back and forth. We are restricting it. The restriction will be automatically C11. It will be C21 locally as well, because we know that it is C21. So if we know, for instance, but we know for sure that the value function is C11 in the measure variable, that is a classical solution for the Hamilton-Jacobi equation. Then we understand the regularity properties of UM. Having this kind of fine estimates, this translates to the regularity of the value function. And this regularity is already enough to differentiate the Hamilton-Jacobi equation on the Wasserstein space, hence having a classical solution to the vectorial master equation. But the regularity of U doesn't follow immediately. So remember that this was linked to this finite dimensional optimal control problem along the optimal flow of measures. So we have to understand this Hamiltonian flow as well. So this is also in some sense part of it is the state variable or the Q variable in the Hamiltonian flow. So if we understand the regularity of this flow with respect to the initial measure, where you see that this flow is generated by the gradient of the value function capital U, then using this kind of techniques via finite dimensional approximation, we can deduce the regularity of the value function as well. So this needs additional effort to show that this little u function is also behaving nicely along this sort of Hamiltonian flow, and Hamiltonian flow is also regular in this sense. And as a conclusion, we can obtain that this little u function is C11 locally with respect to all the variables, and for arbitrary long time horizon, and master equation has a classical solution in a pointwise sense. And with this, I will thank you for attention.